Hello everyone, welcome back to the channel. Today we'll be solving one of a medium problem from lead code, bitwise and of number range. It's problem number 201 in lead code. And let's go to the problem. The problem states that we'll be given two integers left and right, wherein we'll have to compute the bitwise and of all the numbers in this range from left to right, inclusive of both the integers. Uh, for the first example, uh, left is going to be 5 and right is going to be 7 and the output is 4. For the second example, left is 0, right is 0 and the output is 0. Left is 1 for the third example, and for the third example, the right is 214748367 and the output is 0. Let us let us do a dry run for these test cases and start off with our approach. Disconnected. There's some network error. Okay. Okay. So for our first example was L is equal to 5, R is equal to 7. So representing these two numbers in binary format, 101, 110, because this is for 6, 6 is in between 5 and 7, and 111 is for 7. So when performing AND operation, 1 and 0 becomes 0, and again 0 and 1 becomes 0. 0 and 1 becomes 0, 0 and 1 becomes 0. 1 and 1 is 1, and 1 and 1 is 1. So the output is 4 as per given in the test case. So the brute force way of solving this problem is going to be very simple. Start with an integer, check all the represent that in the binary format, check with all the digits in the binary representation with the other integer 5 and 6. For let's say we calculated from LSB to MSB, and finally compute your answer. But obviously, this is not going to be the most efficient way of solving it. Thereby, we'll discuss the most optimal approach. So the most optimal approach involves key observations, which we'll be checking. We'll be looking into now. So, what are the key observations? Observation one is uh, check for the common prefix. Observation two is number of digits. Okay, so let's go for observation one, common digits. What do I mean by common digits is that let's say L is equal to 5, R is equal to 7. We have 11101, 110, 111. Common prefix for these three numbers is 1. So whenever you see a common prefix, it's going to be same. That uh, part is going to be same. So you can simply directly write that 1. The remaining part, whenever there's a mismatch between the digits, the rest of the part is going to be 0. Um, let's try for another test case wherein L is equal to 4 and R is equal to 6. L is equal to 4 and R is going to be 6. So the binary representation of 4 is 100. Uh, the binary representation of 5 is 101, 110. Common prefix 111. 1 is the only common prefix here. So just simply directly write there as 1. The remaining part is going to be 0. So if you can compute it manually, we'll be getting answer as 100, which is 4 again. So the bitwise and between 4 and 6 is 4. Okay. Uh, this is the observation done for common prefix. Next observation is for number of digits. So let's say I have okay. Let's change the name, change the range of the numbers. It's going to be 3, L is going to be 3, and R is going to be 5. So 3 can be represented as 111 1011 4100 5101. Maybe you can remove 0 here. Still, it's going to be 3. So what is the observation is that 3 is the number of digits when 3 is represented as binary. The binary form is lesser than the subsequent numbers. It has only 2 digits, but these two numbers have 3 respectively. Thereby, uh, there is not going to be any common digit for all these numbers. So you can simply written 000 everywhere. It's going to be 0 for sure because there is no common prefix. Let's take another example. 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's take for L is equal to 6, R is equal to 8. So 6 is 110, 7 is 111, 8 is 1000. So 8 has 4 digits, whereas 6 and 7 has 3 digits. Thereby, the overall answer is going to be 0 anyways. Because you add here 0, you add here 0. Even though 6 and 7 has a common prefix, but it is not common with 8. Because our range is from L equal to 6 till R equal to 8. Thereby, our answer is going to be 0. So instead of checking for the number 7 or any other number in between L and R, we can simply check, uh, we can simply get our answer just by looking at the L and R and making some operations. So how do we actually arrive at finding the common prefix? Let's say I have 101 and L is equal to 5 and R is equal to 7, and this is 5. 110 is no, 111 is 7. So we'll be going from least significant bit to most significant bit. So we check this one. If this one, first we check, we first check if both these numbers are equal. No, they are not. We remove these bits. Now it's going to be 10 and 1. Are they equal? No. We remove this. Are they equal? No. Yeah, after removing these two, they are equal. So we just break out of the loop. So the loop runs till whenever the numbers are not equal, we keep running the loop. And we'll have a counter variable to check how many uncommon digits are there for these two numbers. Let's say, let's make it more clear by taking the same example. L is equal to 5, R is equal to 7, 101, 111. And there is a counter variable named C equal to 0, while L while L not equal to R we'll be going from least significant to most significant. Thereby, will be whenever it is not equal, we'll reduce these bits. So our at the first time, 5 and 7 are not equal. Thereby, our integer reduces to 1 and 0, and counter increments to 1. And at the second time, ln r are not equal again. So we remove these two digits, and the counter increases to 2. Thirdly, the third iteration we check, yes, they are equal. So we break out of the loop. After breaking out of the loop, we got C as 2 because there were there were two uncommon integers for these two numbers. That is, after after you find the common prefix, everything as is going to be zero. Everything is going to be zero. From the observations we made in our past. Let's try it for another test case. L is equal to R is equal to 3. So there are only two numbers between this. 0. It can be represented as 1 0 1 1. Common prefix is 1. This is 0. So the bitwise AND range between 2 and 3 is 0. 1 0. Sorry, that is 2. So at the end, once you find the uncommon number of integers between L and R, you simply return answer uh, whatever the answer you have, no, whatever the R that is remaining in our answer with the number of add the number of zeros in the L. So to make it more clear, L is equal to 4, R is equal to 5, 4 is 110, 100, 5 is 101. We first check if 4 and 5 are not equal or not. No, they're not equal. Increment counter to 1. Remove this. Uh, is 10 and 10 equal? So these two are equal. Thereby, we break out of the loop, and our C is going to be 1 again. So what was our R? R was 1 0. So 1 0 of we add uh, a 0 to it, because C is 1, we add a 0 to it, and our answer is this 4 again. So I hope you understand the intuition behind this. So let's quickly code it up. So this is my I initialize my counter variable to 0 while left not equal to right, left equal to left. Uh, uh, this is a bitwise and of this is a right shift operator. So what it does is, uh, let's say I have 100. When I use right shift operator, it is gonna get rid of this bit, and in the next iteration, this is gonna get rid of this bit, and in the third iteration, it's gonna get rid of this bit when you use this. Right equal to right, and count plus plus. What you do is you simply return right. Right is the common bit that we are going to have, and the remaining uncommon bit are stored in the variable count. So let's run it. Accept it. Let's submit it. Oh, oh, it should be count, not two. Now if you submit, it's going to run completely fine. 527, accept expected output is 4. Mm, it's 1 here, not 2. Accept it. Accept it. So I hope you like this video and you understood the content. If you really uh, didn't understand anything from what I explained, you can please post your comments over there. I'll definitely reply to all of your comments. Thank you so much. Have a nice day.